And
Hello.
right here. Hello, Adam. So
Yeah.
to introduce Adam to our viewers here, Adam is a CTO of a company called Software Mill, which he co-founded. He mainly codes in Scala and other interesting technologies from what I've heard. So I can also let you say a few words about yourself just before we begin.
Sure thing. So thanks a lot for coming, and thanks a lot for having me here. Yes, my name is Adam Warski. I'm coming from Warsaw, Poland, so quite far away probably for most of you. And yeah, I'll be talking about Project Loom and better futures. So I guess we can start.
Yep,
I've
go
shared my
for it.
screen. If there's
Go
anything wrong,
for it.
let me
Oh,
know.
no, that's not the one. Let me see. Could you share your screen? Oh, there it is.
Yeah, I did. Okay. Okay, we are good to go then. Let me go into full screen here. Okay, so welcome again. Again, thanks a lot for coming. So we will be taking a look at Project Loom, but before actually diving into Project Loom, we will take a look at futures, and we will try to understand why have we ended up using futures in the first place. And once we have that foundation, we will see what Project Loom is all about and what might be coming next for concurrent programming on the JVM. So first, it's good to state the problem that we are trying to solve. So nowadays, it's quite often necessary to run multiple processes concurrently. So we want to have multiple threads of execution to run at the same time. And that is not a trivial problem. It's not an easy task. There's a number of approaches to do it and a number of ways in various languages, and they bring various problems. In Java, we have a couple of approaches. Also, there's a lot of JVM languages which take different approaches. So the solution space is quite vast, and Loom is trying to improve the situation in Java and on the JVM, because Project Loom will be usable in all JVM languages, not only in Java. So that's the problem that we are trying to solve. And when we are talking about concurrency, it might be beneficial if you can think of some examples. So some examples of concurrency that you meet in real life, I guess the most obvious is processing concurrently multiple HTTP requests. So you have a lot of users trying to connect to your service, and you need to process these requests concurrently. Or maybe another example would be processing messages from a queue. So you have a message queue with some tasks to run. And again, you need to process these messages concurrently. Maybe you are integrating external services. So you need to call some APIs, and you might need to call them in parallel as well to speed up execution of your workflow. And speaking of workflows, you might be orchestrating whole workflows. So you might have multiple workflows running concurrently, and you might want to communicate between them. You might want to run multiple workflows at the same time. Or background jobs, another common example of concurrency. So when we are talking about concurrency, you can think about these use cases to make the examples a bit closer to real life. So in fact, the crux of the problem isn't only that we want to run processes concurrently, but we want to run a large number of these processes. So why do we want to run a large number of those? So there's two reasons for that. First of all, it might be necessary. So it might be a business requirement that we actually need to run a large number of processes concurrently. So maybe we need to process a lot of HTTP requests. Maybe we need to service a lot meaning thousands or tens of thousands, a lot of WebSockets concurrently. These are typically long-running processes. So it might be a business requirement, but it also turns out that it's often easier to build concurrent programs when we can work with very small processes and when we can compose these small processes into larger ones. It's also, from a programming model point of view, it might be beneficial for the overall program readability and understandability, explorability, and so on, to have the liberty to create a large number of concurrently running processes. So these are the two reasons why we actually might want to run a large number of processes concurrently. So what's the current situation on the JVM? So currently, the basic Unicode of concurrency in Java is a thread. So these threads, the threads that you start in Java, they map one-to-one to kernel threads, so to threads in the operating systems. And this has a couple of downsides. So first of all, a kernel thread, and hence a Java thread as well, is expensive to create. So it takes a non-trivial amount of time, and it takes some memory because we have to allocate a stack for this thread to actually create a new kernel thread or a Java thread. These threads are also expensive to switch. So it takes, again, a non-trivial amount of time to switch execution from one thread to another. And there's a limited number of threads that we can create. So it's still like in the thousands probably, but probably once you try to create tens of thousands of threads, you might run into problems. So these kernel threads are quite limited. So we will have to somehow work around these limitations, and we will see solutions that try to work around these limitations. So before we dive in further, I would like to, I've had the introduction already, but I would like to give you some background on why actually would I be a good person to talk about concurrency. As already mentioned, I'm the co-founder and the software engineer at Software Mill. We are a company which helps businesses transform their companies through software. I've got 14 or already 15 years developing backend applications, starting with J2E through Spring, with some episodes trying to do concurrency manually, but that's quite tricky. And then going more into functional programming using Akka, Scala, and other languages and frameworks. I'm also an open source contributor, so I've created a couple of open source projects, HTTP clients, servers, utility libraries. Hibernate Enverse is a module for auditing entities, so quite a broad variety. And the main things I do at our company is working on distributed systems, systems which use messaging. So we deal quite a lot with concurrency and concurrently running processes. Okay, so once we have this background, let's look at what are the current solutions to the problems with threads and the fact that kernel threads are expensive both to create and switch. So a solution that came to Java a long time ago is to actually create the threads upfront. So when our application starts, for example, we create a pool of threads that we will be using in our application. So we usually a thread pool is represented by an executor service or something like that. So we create a pool of threads that will be executing tasks for us. And thanks to that, we don't when we have a task to execute, we don't have to create a thread. We just take a thread that's already in the pool and is already created, and it can execute our task. And each task that we submit to such a pool for execution has to run to completion. And that has some downside, because if each task if we submit long-running tasks, that will actually limit the concurrency, right? Because if we let's say we have a pool of 3 threads because we have 3 cores on our computer, and we submit 3 long-running tasks, this will actually block all available threads. So if we don't want to limit concurrency, we should actually take care not to submit long-running tasks, but create small, fine-grained tasks. And once we create small and fine-grained tasks, we need a way to manage them, to stay sane, and we need somehow some way to compose them to build bigger programs. So putting it a bit more graphically, let's say we have a task queue over here of tasks. You can see that some of them run for a long time, some are very short. And here we have 3 threads that execute our tasks, right? They take tasks. So if this thread finishes executing this task, so once it goes all the way to the bottom, it will take the next task from the queue. And here you can see that the tasks actually, we have 3 long-running tasks. So before we get into executing these quick tasks, which would just take very quickly to complete, we have to complete those long-running ones. And if we look a bit closer, quite probably these tasks take a long time because they are sleeping or waiting for some I/O events. So quite often, if we are using blocking I/O in Java, if we have a thread that's running that takes a long time to come, if we have a task that's taking a long time to complete, most of the time it will probably be sleeping, waiting for like opening a file or reading from a file, reading from the network, sending something to the network, or just sleeping, waiting for some condition to come true. So that's a waste. All these thread areas are a waste, right? Because these threads are idle, they don't do anything. So that's where non-blocking or asynchronous I/O comes in, right? We need to chop down these tasks into smaller ones and avoid these idle pauses. So the way more or less it works is that we have our task queue. That's these are the tasks that are waiting to be executed. But when we want to do I/O, we actually break down the tasks. So here you can see that there's a task that does some computation, and then it executes an I/O operation, right? And this I/O operation will have a continuation. Once it's done, this will, for example, maybe here, this will be the continuation of the I/O operation. But these tasks are much smaller. So when a thread when a thread executes a task and encounters an I/O event, it will actually put the rest of the task to an I/O event task queue. So here we have tasks which wait for some I/O event to happen. For example, they wait until the file is open, or they wait until there are some bytes to read from the network, and so on and so on, right? So we don't block these threads waiting idly until I/O or some condition is happening. And that's more or less how asynchronous I/O works. And the way these boxes are implemented in Java is usually through completable futures. A completable future is a value, which is very important. It will be also important later. So that's a value that we can, assign to a variable and so on. And it represents a computation that's already running in the background. So it's something that's already happening. And eventually that computation will yield a value of type T, right, which is specified here. So it's like a box that will eventually be filled with a value of type T, or it will end with an error. So now with asynchronous or non-blocking I/O, what we get is when we try to read from a file, we actually get back a completable future. So that's the continuation, right? That's what we get is a continuation. So this piece over here of what should happen after that I/O operation completes. So that's why we ended up working with completable futures to implement non-blocking I/O, to avoid blocking threads, and to increase the concurrency of our thread pools, which has both benefits for performance, but also for the programming model. And the nice thing about futures, there's a couple nice things about futures. They are very cheap to create. So unlike threads, which are expensive to create, they are very cheap to create. We can create a large number of futures, and we are only limited by the heap. They are also cheap to switch, so we can execute multiple futures concurrently, waiting until the conditions complete. Also, futures are composable, so we can build programs which result in a future from smaller futures, right? So that's a very nice property. It's like Lego blocks. If you want to build a big construction from Legos, you start from multiple smaller ones and you build bigger and bigger ones. So futures are similar, and we can compose futures in two basic ways. So first of all, we have parallel composition, right? So here we are starting two computations in the background. So we are starting one computation. Well, there are trivial computations as an example, but let's imagine that this actually is some expensive I/O intensive operation and so on. So we are creating two computations, and these two will run in the background concurrently. And then once they are ready, we combine their results, right? So these two futures will run concurrently or in parallel if the underlying hardware allows it. So that's the first way we can compose futures. The second way is we can compose futures sequentially. So we can say that first run this future, and once this future completes, we get the result of computing this future. So this will be 42 in this trivial example. And then we create another future that should be run after it, and this future depends on the result of the previous one. So that's sequential composition. So that's like first do this and then do this, right? So that's like the most basic building block of any imperative program which has a sequence of instructions. So that's futures that we've come to work with a lot. And you know, they're nice on one hand, but not so nice on the other. So life used to be simple in a way, right? If we had this very simple code to activate a user in a database, right? So we have a method which takes the ID of the user, looks up the user in the database, and if the user is found and not yet active, then we activate the user and return true, saying that we've succeeded, right? Maybe it's not the best API, as Mario pointed out, but well, that's just an example, so we don't have to be very, very elegant here. So yeah, it's easy to understand what this method does, right? But now you can see that here we actually have blocking operations, right? So this database.findUser will probably do an IO operation, so it will try to connect to the database, run a SQL query, and so on. So this might be expensive. So if we want to use non-blocking IO, if we want to run a lot of those, of such requests concurrently, we probably have to use completable futures, at least if we are using Java today, right? And this code becomes something like this. Now we have database.findUser, and this no longer is a blocking call. This returns a completable future, which will be complete with the found user eventually, right? So then we have to use sequential composition to compose it with the rest of the program when the user is found. And here again, when we activate a user, that again returns a completable future, and then we have to compose it sequential with the rest of the program, which should be run after the user is activated. So it's no longer so, at least for me, that's much more readable, and that's much more obvious what the code should do from like a business logic perspective than this one, right? This one is non-blocking, and you can run it concurrently and so on. So it has much better technical properties probably, but it's less readable. And as a result, also the method returns now a completable future. So these futures are quite viral. So they like infect your code, and once you start using futures, you have to propagate them higher and higher. So futures are nice because they are, you know, cheap to create, and they compose in parallel or sequentially, but there are also some problems with futures. One problem is that we lose the control flow, so we lose the nice overview of how the code should be running. We lose the context. So if we go back over here, if an exception happens over here or over here, we will get in the stack trace the exact location of and the exact sequence of invocations of what actually happened and how we got to that method activate user, right? So who called it and so on. If an exception happens here, the only thing we will get is a stack trace to the thread running the current fine-grained task. So the stack trace won't be informative at all. So that's why the context is lost here, right? And as I said, the futures are viral. And that's where we get to Project Loom. If we read about Project Loom, its mission statement is to drastically reduce the effort of writing, maintaining, and observing high-throughput concurrent applications that make the best use of available hardware. So that's a very good mission statement. Let's take a look at what it means in practice. So the first contribution of Loom are virtual threads. So a virtual thread is just like a Java thread, but it's cheap to create and block. So it's no longer bound to a kernel thread. We can start a virtual thread in a very similar way as we start a normal thread. Instead of, we just use a different method. And this will actually start a virtual thread that runs the given computation in the background, but it isn't bound to a kernel thread. So it doesn't mean, so this operation is cheap and it's fast. It doesn't start a kernel thread in the background. It will actually, behind the scenes, it will use the same mechanism as we have talked about it when using futures. So behind the scenes, there's an executor service which has a pool of kernel threads on which these virtual threads will run. So we can run a large number of virtual threads on a small number of kernel threads. So that's the first contribution of Project Loom. And that's not entirely a new idea. In other languages, this is known as fibers, or Go routines in Go, or coroutines in Kotlin, or processes in Erlang. So this kind of construct is well known, and now it's coming into Java. It's of course it's coming into Java in a flavor that's compatible with the whole Java philosophy and ecosystem. So that's the first major contribution of Loom. And the second is retrofitting existing APIs. So one major problem we had why we started using futures is that we had blocking operations which blocked kernel threads, right? So for example, reading from a file was a blocking operation which could cause a thread to be idle and just wait until that finishes. And that's why we were using non-blocking IO to actually chop down our tasks into small ones. So Loom tries to fix that as well, and it does that by retrofitting existing operations so that any operation that blocked the kernel threads now becomes non-blocking. So in reality it blocks a virtual thread, but blocking a virtual thread doesn't mean that the kernel thread is being blocked. It just means that the virtual thread will be suspended, it will be put aside, and we will wait for the IO event to actually complete, for example, or some other condition to complete. Very similarly to the IO event queue that we saw with futures, but this time this is done on a different level with nice syntax and without the problems of lost control flow and so on. So if just to give you some examples of what kind of blocking operations Project Loom makes non-blocking. So for example, if we have an input stream, we call the read method. It will read some bytes from the input stream, right? So this used to be blocking, and this used to block the kernel thread. So that was, if you are doing non-blocking, if you are doing concurrent programming on the JVM, you could have developed a kind of a fear of such operations. So now this will be non-blocking. Same for writing using a writer or acquiring a semaphore, right? This used to be a blocking operation. Now it will block the virtual thread, but it doesn't translate to blocking the underlying kernel thread. Or even sleeping. That's also a common operation, right? We need to sleep to wait until some condition comes true, to check again, to send something to the user after a delay and so on. So that's not an uncommon operation. This will also be a non-blocking operation. And to give an example of how this works in the background, so again, we will have a pool of the kernel threads that started when the JVM starts, and we will have a small number of kernel threads, and we will have a large number of virtual threads. So here on this picture, each virtual thread has a different color. So you can see that we have the yellow one, the virtual threads runs here, then it yields. So maybe it waits for some IO operation to complete, right? It's put aside. And then once this IO operation completes, it's resumed. It can be resumed on a different thread. It again runs, then it again is suspended. So it yields the control, and then it is continued on another thread, right? And we can have a lot of these virtual threads running on a small pool of kernel threads, right? The only thing is that each kernel thread can only run one virtual thread at a time, but because they are continuously yielding and resuming, we get good concurrency. So Project Loom also includes continuations and tail call elimination, which will come later. But continuations are a low-level construct with which virtual threads and the retrofit is implemented. So we are not going to be concerned with it. Just so that you know that it's also in scope of that project. You might be wondering, when is Loom coming to Java? Well, that's a very good question, and I have no idea. The project started in 2017. It's much of a research and exploratory project, so there were a couple of different approaches into how actually implement these virtual threads of fibers as they were known before. Currently, I think it's coming to a stage where it will actually become part of Java. It's available in early access, but it's still subject to change. So I think that, especially given that Java is released every 6 months now, we can hope that Loom is coming sooner than later. But again, I'm not from Oracle, and I simply don't know when it's going to happen. So we saw some problems with sequential code being converted to futures, and how this actually caused problems with lost control flow, with virality, and with lost context. And Project Loom is great to actually untangle this kind of code, right? So if we have sequential code, so if we have a sequence of operations like find a user, check if the user is active, and activate the user, so that's a sequence of 3 steps, Loom will be fantastic to actually untangling this kind of code and bringing back the old readable, clear code that we know from the old days. But that's only, so we will be able to kind of to go back to old days and just write code like that. But that's only half of the story, because here we are doing sequential operations. So, and if we are doing sequential operations, great, we just use these blocking. So again, these operations, they seem like they might be blocking, and they do block virtual threads, but in the background, in fact, they are non-blocking. So for sequential code, it's great, but what happens if we actually have concurrent code, if we have some processes which we want to run concurrently and communicate between them, right? So here things are not that easy. So well, a virtual thread is still a thread, and programming threads is tricky, and it's error prone, and many people have tried programming threads and have failed. So there's some gotchas that you have to watch out for. So while Loom is really great for untangling this sequential-like code, you have to remember that it still operates on threads. So it's still quite a low-level concept that we are dealing with here. So what are the problems with threads? So we might want, if we are running a couple of processes concurrently, we might want to communicate between them. So we might want to send some data from one process to another. We might want to orchestrate the threads. So we might want to run these threads in parallel. We might want to start them after a delay. We might want to interrupt threads if they are doing unnecessary work. And there's a couple of patterns that are quite common. For example, here we have a process which forks into 3 processes running in parallel, right? So we have 3 processes running concurrently in parallel. And then once all of these 3 are done, well, they're running concurrently, not necessarily in parallel. So once these concurrently running processes are done, we collect the results of all 3 and we continue, right? So here we have forked into 3 processes to speed things up. Or we can have arrays. That's another common pattern. So we can have a process which then forks into 2 concurrently running processes, right? And it's a race. So whichever one completes first wins, and we take that value and we interrupt the other one. As an example here, we might have an operation which looks up a value in the cache or looks up the value in the database. So whatever completes first is returned to the user, right? And the other needs to be interrupted. So that's another kind of concurrent pattern that we see. Or we might want to run some task in the background, continuing our normal stuff, right? So here we run something in the background and eventually want to get the result of the background application, of the background process. So these are like the basic building blocks, but in reality, they can get very complicated, right? So we can have arbitrarily complex networks of processes which send data to each other, interrupt each other, and so on and so on. So we need a way to model these as well. And well, there's a couple of low-level tools which we can use for thread communication and synchronization. So here, when I'm talking about threads, I'm really talking about virtual threads or threads, like whatever is so Loom kind of changes the basic unit of concurrency, right? Before Loom, the basic unit of concurrency in Java used to be kernel threads and the Java threads which are bound to them. Now these are virtual threads, which can be of which we can have a lot more. So there's a couple of low-level tools which we use to communicate between threads. These are semaphores, logs, queues, channels, things like that. And it is possible to do concurrent programming using these, but probably you'll quickly find out that you have run into a deadlock, so where threads wait for each other and nothing is happening, or race conditions where threads actually race which one is first to get some value, but that's not something you intended, but an error, and weird things start happening sometimes, not always, because concurrent bugs have this unpleasant characteristic of happening only sometimes, probably most often in the wrong time. And people again and again discover that concurrent programming is hard, and it is hard for a reason. It is hard for a reason because it's the number of states in which your code can be grows exponentially if you are dealing with multiple processes running concurrently. So you're never really sure what exact state your system is in, and modeling all of those is really hard, if not impossible. So maybe for concurrent programming, futures aren't that bad. So let's think again, what was it that was good about futures? Maybe we can retain some of these characteristics. So the performance was good, right? Because we were able to run multiple processes concurrently on a small number of threads. The programming model wasn't that bad. Well, it was bad when talking about sequential code, but when modeling concurrently running processes, it was much better, because the futures, if you remember, they are a composable construct. So we can compose them in parallel or sequentially, and this gives us a basic building block of actually building more complex APIs. And actually, one way to avoid, and one way to reduce, at least, maybe not avoid, one way to reduce concurrency bugs is avoiding using threads directly, either normal threads or virtual threads. So let's see how can we do that. So what we really want to do is we want to use declarative concurrency. So we want just to declare how our processes should run, what's the shape of the network, and how the communication more or less should look like. So what values, what processes we need, instead of specifying exactly how this communication should happen. So we don't want to deal with semaphores, locks, queues directly. We want to avoid it, right? And futures give us a tool, and then maybe we can use that tool in combination with Loom, right? So futures give us the basic building blocks, sequential and parallel composition, and libraries can actually provide us with high-level combinators. So let's look at an example, right? Very simple task. We want to fetch in parallel data from two URLs. So we will want to send one request to a profile service to get the profile of a user, and one request to a friends service to get the friends of a user, maybe some microservices. And we want to run these two requests, these two HTTP requests in parallel. So we are using Loom. So here we have the version based on virtual threads. So we have a method to send an HTTP GET request and retrieve the contents of the given URL. And it's a normal blocking method, right? We are in Loom, so we can block. We are only blocking virtual threads. So this is all nice and easy, right? We also need, because we will be running two processes in the background, and these will run in parallel, we need a place where we will store the results of each of the invocation, right? So that's like a cell. It's like a memory cell which will store the results of our of fetching that page. And we also need a latch which will count down, and when we will, so the main thread will have to know when both results are done, right? So we will have the main thread which will run two child threads, and these two child threads will run the requests in concurrently. And then once they are done, they have to let know the main thread that they're actually done and that the results are in the memory cells. So we need these two constructs. And then here we have, so we start a virtual thread, right? So this will happen in the background, comparing to the main thread. And what we do here is we call our HTTP GET method on the profile service in a blocking way, right? In a virtual thread blocking way. And then we set the result in the memory cell. And when we are done, we count down the latch, right? That happens the same for the friends service. And in the main thread, what we have to do is we have to wait for the countdown latch to actually complete. And once this happens, so again, that's a blocking operation that blocks the main virtual thread. And once this is done, we can get we can combine the results into some data structure that we return to the user. So that's quite a lot of machinery, quite a lot of boilerplate to run two things in the background. Let's see how we can do the same with futures. Well, with futures, an API that you can probably use today is we have a different signature of the method used to actually invoke the HTTP GET request, right? This is an IO operation which happens in the background asynchronously. It uses asynchronous IO. So as a result, we don't get a string, but we get a future of string, right? So this is we will get a computation which will eventually be complete with the result. And we call the profile service, right? So that's the first feature that we create. We create the first computation in the background, and then we create the second computation in the background, and finally we combine the results into one once both of these are ready. And this is considerably simpler, right? So while Loom transformed the future code into the blocking version of the code, and in the sequential case, and it was much nicer, when we have to run two processes concurrently, the future version is much nicer. So there is some place for middle ground and maybe combining these two. So it's probably not surprising that no style fits all use cases, right? So sometimes it's better to write synchronous or blocking-like code, right? So sometimes it's better to work with APIs which block the virtual threads, and it's easier to express our business logic that way. But if we want to orchestrate some concurrently running processes, it might be better to operate on futures. So let's now speculate a bit. How could we maybe combine these two into a more user-friendly API? So again, this doesn't exist. It's just pure speculation. It's invented code, but let's see how it could look in the future, right? So again, we are back into the Loom world. So we have our HTTP GET method is blocking virtual threads. So the result type here is a plain string, but we have this run method that's provided by a library. And it takes a piece of code to execute in the background, right? And it as a result, we get a completable future. And this code over here, it might be blocking. In fact, it is blocking virtual threads because it sends an HTTP GET request, but it runs in the background, and this run method actually takes care of creating the memory cell where the result is stored and for actually completing the future only once this method completes. We do the same for the friends result, and we then combine them. So again, here we are using Loom, so we can just call .get on the future to block until the future is ready. So first we start two computations running in the background. So we create two futures, and then we combine the results. So that's much better, right? But we need this library code to actually provide us with the better tools to manage concurrently running processes. And if we speculate even more, maybe we can have a library which exposes a run parallel method, and which will allow us to just give it a list of runnables which will or callables which should be run in parallel, and a method to combine the results. So that's even nicer, right? But that's again a library method that should be provided, which combines the benefits of Loom with futures. So yeah, so we have seen why futures are good. We have seen why Loom is good, right? Loom gives us tools to write non-blocking way in a blocking style, and it's both a matter of syntax. So syntax matters a lot when it comes to the readability of the code, and simple APIs matter a lot. So thanks to Loom and thanks to the retrofitting of blocking APIs into non-blocking ones or into ones that block virtual threads instead of kernel threads, we get access to the simple APIs that like input streams, readers, writers, thread.sleep. These are simple APIs which express the intent quite clearly. So we can once again use them using nice syntax. So that's what Loom gives us, and that's the benefit of Loom. What Loom doesn't give us is a total replacement for concurrency libraries. We will still need them to describe our concurrently running processes. And if we take another view on that, we can represent a process as in two ways. So we can look at the process as code. So that's using a piece of code, sequential piece of code written using the blocking style. So that's one way to view a process. And another is to view it as a value, right? A future was a value which was representing a process which runs in the background. And once we have a value, we can compose it with other values and so on. So we are quite good working with values all the time in your business code. You're working with values which represent users, orders, products, whatever. Why not working with values which represent computations, right? So, and sometimes it's easier to look at a process which runs concurrently with other processes as code, and sometimes it's easier to look at it as a value. And actually, this duality is also well known, so it's nothing new. And futures are just one important step in the evolution of writing concurrent processes. If we think a bit of what kind of high-level operations we might expect from a library operating on futures, we might expect to get a retry method which runs the given future again and again until it succeeds or for a given number of times and so on. We might expect methods to run things in parallel, to race between two futures and so on. So if we think about them, we will often operate on, so the computations that are passed to these high-level methods will be callables. So these are not computations that are already running, but they can be run on demand. So they're like lazy computations, right? Or they describe a computation. So we will probably be operating on a callable, and we will be creating some abstraction on top of callable to actually implement our retry, run in parallel, race operators, and so on. And that's, again, not a new thing, and many libraries and languages have already done it. And in the functional programming communities, these are quite often known as IOs, data structures. So just as here we had a value of type future, which is an eagerly running process, we can have a value of type IO, which is a lazily running process, right? A future represents a running computations, something that's already happening. It's happening eagerly, right? On the other hand, an IO value is representing a description of a computation which is lazy. And again, futures are a very important milestone in the evolution of concurrent programming, both on JVM and in other ecosystems. And IO is the next step of that evolution, because it turns out that operating on these lazily evaluated descriptions is often much easier, and we will see an example of how this works a bit later. So before concluding, I would also like to touch on one more subject, which is cancellation. And when we talk about concurrently running processes, cancellation is often overlooked, but it's a very important concept. So we've grown to become afraid of interrupting threads in Java. But it's not because the whole concept of interruption is wrong. So the basic example of racing two processes, one looking up things in a cache and the other looking things up in a database, right? Once we looked up the value in the cache, we need to interrupt this database process because it's doing work that's not needed, and we can probably do something else that's more useful. So we need to interrupt it, right? And so the concept is useful, but the implementation so far was quite error-prone. So it's quite dangerous to actually interrupt threads in a thread pool. So that's why we've been advised not to actually use thread.interrupt in Java. However, with Project Loom, this once again becomes useful because Project Loom also covers also fixes also rather enables interruption on virtual threads. So we can once again use this mechanism. And with the problems of cancellation or interruption also comes the concept of finalizers. So we often need to do something always after a code block completes successful or not, right? For example, if we are running a query against a database, regardless of the fact if it completed successfully, if it ended with an error, or if the process was interrupted, we need to always release the connection back to the connection pool, right? So that's a code which must always run. Or maybe we need to notify some observers and so on. So these finalizers are a very important concept, which is always coupled with the concept of cancellation. So as an example here, right, I was talking about the race. So we can have one process which is racing with another process. So if this process wins, it will actually interrupt the other process, right, in a race. And so that's the amount of work that has been prevented, which is unnecessary, but there's still some finalizer that must run and clean up any resources acquired by this process. And then execution can continue normally. So how can we implement interruption using Java and Project Loom? When one obvious candidate is using thread interrupt, because thanks to Project Loom, it now works using virtual threads. But how can we implement finalizers? Well, our first approach could be to use try and finally, right? And anything that's in the final block will always be executed. But will it? Well, what happens if we cancel finalizers? That's not so obvious, right? What happens if the interruption comes when the finalizer is run? And it always needs to run, always, always. There's no exceptions, right? So it's as far as I know, it's an unsolved problem so far, in Loom at least. So some solutions that we might see here are defining uninterruptible regions. So for example, the code in finally maybe can be somehow defined as being uninterruptible, or maybe we should use a different finalization mechanism in the presence of interruption. Maybe we need a coordinator. So there's a lot of concurrency libraries in Java, Scala, Kotlin, and so on, which introduce the concept of a coordinator, which coordinates which tasks run on which thread pools and so on. And the coordinator is needed because we don't have the mechanism, the virtual threads that Project Loom gives us. But the coordinator also makes sure that any finalizers are really run when they have to run. So summing up, where Project Loom shines is implementing business logic in a readable way. So if we have, for example, let's say we have a task to find a user with a given ID, and if the user exists, activate it, and then return a flag specifying if the user has been activated. So Project Loom will be great to writing this type of code in a nice, readable, sequential way, right? Any exceptions thrown here will have the full context. We don't get any virality of the futures, right? Because, well, it's just normal code. It reads nicely and so on. On the other hand, if we have tasks where we need to orchestrate multiple processes, right? Let's say we have a task that we need to look up a value in the cache, and if no result is returned within 100 milliseconds, we need to look up the value in the database, right? So we introduce a delay before going to the database. And regardless of whichever completes first, the first result should be returned, and accessing the key should always be reported to some metrics system. So that's a description of a concurrent process, and it would be, of course, possible to implement it using Loom, semaphores, queues to communicate between the processes, but it would be hard. So here, the declarative approach, so here the example is using Scala and the Zio concurrency toolkit. So here the declarative approach is much easier, right? We describe the process as a value, right? So we have one value describing looking up things in the cache. That's the lookup in cache method returns a description of a computation, which is also a value of type IO. So that's the first description of a process which we raise, and we raise it against this process over here, right? And this process contains two steps in sequence, right? The first step is to sleep for 100 milliseconds. And once this step completes, then we look up the value in the database. And this again returns a description of a process of type IO. And this IO raise is a combinator which combines descriptions of two processes into one process, which raises those two, right? And at the end, we add a finalizer, which is also a description of a process, so a value of type IO, to report that the key was accessed to some metric system. So this declarative approach reads much better than actually going into the details and implementing this all by hand. And in the background, this lookup and cache, it might be using Project Loom, it might be using virtual threads to implement the business logic of looking things up in the cache. But once we get to orchestrating concurrently running processes, it's probably better to use the declarative concurrency. So we've just scratched the surface of the implications that Project Loom has on concurrency on the JVM. What we haven't discussed, some important concepts are structured concurrency, thread locus, reactive programming, streaming actors. All of these areas will be somehow influenced by Loom, usually in a good way, meaning that code will become simpler and more readable. But these concepts don't go away, right? Loom solves some of these problems, but it doesn't eliminate the need of declarative concurrency. I would say that quite the opposite, right? It's now easier to create concurrent code running on the JVM, thanks to Loom. So we will see the need for more libraries which actually orchestrate the running of these processes and are declarative, and instead of working with these low-level primitives. So if you would like to read a bit more on the topic, there's a number of links over here. I will post the slides on the Slack channel and on the chat and on Twitter. If you would have any questions, you can again ask me on Slack, ask me on the chat, or just ask me on Twitter. My DMs are open. There's a link here to the blog which explains this concept in a bit more details. A link to the presentation if you'd like to take a look. And yeah, thank you very much for listening. I hope this was informative. And yeah, thank you very much for coming.
Yeah, thanks a lot, Adam. That was a very interesting presentation. Let me just go back to this view. So we've got a few questions now that I can maybe read out. We have about 10 minutes for Q&A.
Okay, sure.
So some of the questions that I see are about comparing Loom with like what other languages have implemented, such as Kotlin coroutines, or comparing with concurrency in Golang. And there's also questions regarding like benchmarking, like have we benchmarked like virtual threads and things like that?
Right, okay, so the question about Kotlin is very good. So in Kotlin, we have the concept of coroutines, which is quite similar. So it's also something that works on, well, it's similar on the syntactic level, right? Because it also now allows you to write blocking code if it was non-blocking. So the way it works, it's a compile time mechanism. So at compile time, the code is transformed into a form that actually uses futures or something like futures in the behind the scenes. So in a way, it's just a syntactic thing, and it won't automatically. So one thing that Loom does is this retrofit of blocking APIs into non-blocking APIs. So that's not going to happen in Kotlin, right? We can use a future-based API in a synchronous-like way in Kotlin, but we don't have this backport that Loom gives us. So Loom kind of takes the ideas from Kotlin further and brings it from a compile time mechanism into a JVM level mechanism. So yeah, and but if using Kotlin's coroutines is one way towards is like one step towards what Loom wants to achieve, and another similar approaches would be in JavaScript. We have async await, right? So we can await on promises and promises or futures, yeah, promises. These concepts, these names, yeah, they are easy to mix up because every language, of course, has a different name for some reason. Yeah, so in JavaScript we have async await, so we can await again on these promises. But this only works, and well, JavaScript is a bit different because it doesn't really have the concept of blocking operations, right? It only has the promise-based APIs. So, but yeah, again, it is in a way similar. So JavaScript is in a bit better situation because it doesn't have to backport all of the blocking code into a non-blocking version. And one benefit of Project Loom is actually that any code that use blocking operations and will be run on the new JVM will just use non-blocking APIs behind the scenes, right? It's automatic. You don't have to change anything. You will just use a different runtime, and instead of running on kernel threads, it will run on these virtual threads, which are much faster. As for benchmarks, I don't know. I didn't do any benchmarks, and I'm not aware of any benchmarks being done. So I won't be able to answer here. So yeah, I guess that answers these two questions.
Cool. Cool, thanks. So another question that I see here is comparing reactive manifesto projects, such as RxJava, Project Reactor, and Akka versus the Project Loom. In your view, can these approaches be combined and coexist, or Project Loom will replace them?
Oh yeah, I think they will coexist. So the reactive projects, they are quite often concerned, for example, with stream processing. And again, they provide APIs which allow you to describe how the stream should be processed in a declarative way without going into the implementation details, right? So I would imagine, again, that's speculation, that more or less these APIs would stay the same. So the way you describe the shape of how your stream should be processed, that would remain the same. However, the individual stages maybe of how to process a single element or a single stage of processing a single element, that could be implemented using Project Loom's virtual threads. So we won't have to use futures to implement these processing stages. We will be able to just use blocking code. But the declarative side of actually describing how the stream should be processed, that should I would expect it to remain more or less the same. So I think the reactive libraries will actually benefit from Project Loom, and because you won't have to work directly with futures that much, but you will still describe and define the stream processing, the reactive processing, the same as you did. And same for other reactive approaches, like I guess the main goal of reactive is to put a bound on the resources that you use, right? So you don't want to process too many elements. You don't want to clog the memory if the downstream can't consume them. So that's a concern that remains if you use Project Loom or a normal JVM, and that's still something that needs to be solved. So I think they complement each other. They don't replace each other.
Cool. I think that's a really good answer to that question. So one more I think that we can take here, if I can find it. So you talked about how completable futures make kind of unusable stack traces. And the question is whether Loom suffers from the same issue.
Oh no. That's one of the things that Loom fixes. So that was the lost context problem. So one of the contributions of Loom is that the stack traces will be usable once again. So it has mechanism to actually propagate the context properly when these tasks jump from one thread to another. It's transparent to the programmer, and you won't see it. So you will get a nice stack trace the way you used to. So yeah, that's going likely to be fixed, because it is a pain, and it's, I think, one of the biggest downsides of using futures. However, there are also attempts to fix it for futures. So if you look, for example, at the Zio Scala library that I've shown, it also contains a mechanism which reconstructs from which. So in the Zio we have fibers, not virtual threads, but it's more or less the concept is the same, but it's implemented as a library, not as a JVM feature. And so Zio has this feature of reconstructing the stack trace, so that again it's usable. So even though the execution of these small tasks jumps between threads, it carries information with it. It is a mechanism which has some runtime overhead, so it can be switched off for production, for example. But there are some attempts to fix that for futures as well. But probably Loom will be a better solution over here, because it's a JVM level mechanism, so it has much more chances to be performant than anything implemented as a library.
Yeah, that makes sense. Well, all right. Thank you a lot for your time and your presentation.
Thanks a
I
lot.
think it was really
Thanks a lot
interesting, and
again for coming and for having me. Yeah.
I see a lot in the chats. People are saying thank you, Adam. It was great. So well done.
Thanks as
and
well.
I guess we can now introduce the next speaker then.